Good evening. Welcome, everybody. Thank you for joining us at Introduction to Astronomy talk for the Auckland Astronomical Society online, October 2020. Let's get started. So this is one of my favourite astronomy images. A lot of you will recognise it. It's an image, a photographic image taken by an amateur photographer, Adam Evans, who does some wonderful jobs. And it's a picture of the Andromeda spiral galaxy, also known as M31, Messier Object 31. It's the closest large galaxy to the Milky Way, and it's similar in structure to the Milky Way. So let's just briefly have a look at it here. You can see here a really bright, super dense nucleus of the galaxy. You see the spiral arms in sort of a circular fashion out here, full of gas and dust and stars that form these nice sort of spiral discs, that hence the name spiral galaxy. You can even see a couple of cool satellite galaxies. One up here, that's M32, and M110 down here. But also what's interesting is what you can't see in this image, and that is the galactic halo. There's a large spherical region around these spiral galaxies, as you can see by putting my cursor sort of indicating around here, that you can't see it because it's sparsely populated with sort of dimmer stars and very tenuous gases. Recently, a group of astronomers have been able to study the gaseous and stellar halo around the Andromeda galaxy with some really interesting results. And that's why tonight's talk is titled The Andromeda Galaxy Halo, Discoveries from a Recent Study. So tonight I'm going to discuss their findings. In particular, they found the halo was much larger, far more massive than they ever anticipated, and it's far more complex than they originally thought. I'll then go on to talk about the significance of that finding. It is important for astronomy. But first of all, I want to use that study and this topic as a vehicle, if you will, to revise and discuss just some general astronomy terms and concepts. Just broadly, it is Introduction to Astronomy, and that's what Introduction to Astronomy should be about. I'm going to achieve this by breaking it into 4 chapters. The first chapter will be on the Andromeda Galaxy itself, a little bit about it. The second chapter is going to be discussing those relevant basic astronomical terms, such as, hey, galaxies, what are the main types of galaxies and their structures? The local group of galaxies, what does that consist of? How big is it? And a little bit about quasars. They are relevant with the study. And then chapter 3, we'll talk about the study, its results, and the significance of those results. And of course, chapter 4, we will sum up and we'll give you some homework just to explore things a little deeper. So first of all, chapter 1, the Andromeda Galaxy. So the Andromeda Galaxy, as I've mentioned, let's just work our way through this. Here's the Milky Way over here. You can see it's that nice spiral structure. You most likely will be familiar with it. Then over here, we have the Andromeda Galaxy. And that's just the image down here that I got from the previous slide, so don't get that confused or mixed up in there. So here's the 2 galaxies. Now, the Milky Way is thought to be about 100,000 light years across the diameter of its disk. A light year being the distance that light travels in a year, which at 300,000 kilometers per second, which is about something like 5 or 6 times around the globe, crazy speed. But at that crazy speed, light travels 10 million kilometers. That's 1 light year. So the Milky Way is 100,000 light years across. The Andromeda Galaxy, however, is about 40% bigger in size. It's about 140,000 light years across. Both are spiral shaped, as you can see here. The distance between the two, 2.5 million light years. You might think, whoa, that's a large distance. In actual fact, that makes the Andromeda Galaxy our closest, largest galaxy. We have closer galaxies, but they're only little small ones, like the large and small Magellanic Clouds that are sort of satellite galaxies of the Milky Way. So at 2.5 million light years, the Andromeda Galaxy is the Milky Way's closest, large galaxy. So what can you see with the naked eye? Well, interesting enough, the Andromeda Galaxy is the most distant object that you can see with the unaided eye. You can see it from Auckland. It's probably, you wouldn't want to go much further south. You can just see it hugging the northern horizon, particularly in the springtime. So now is the time to go looking for the Andromeda Galaxy. Good luck to you there. You need to really get a good view, sort of to right close down to the northern horizon there. And this is what you see here. This is an image as you'd see it. And that bright smudge is that really bright, super dense central nucleus. So let's just go back. See that bright little bit right there? Let's just go back a couple of slides. That's what we're seeing. That's bright enough to see, but we can't see all the stuff here, the spiral structure. It's not bright enough for us to see with our unaided naked eyes, without a telescope, at 2.5 million light years. But yep, we can see as a small smudge that super dense central nucleus. So what would it be like in the sky if, say, it was bright enough? It's current distance still, but let's just imagine that spiral structure was brighter than it is. What would we see? That's what we would see. That's the scale. Isn't it amazing? And how about if we do a close-up on that and just bring that a little bit closer to the moon to give us a better perspective? Whoa, look at that. So it's a pretty large galaxy, as you can see, 140,000 light years across. So that's what it would look like in the sky if it was, say, compared with our moon, if we could see the disk structure. So, as I've mentioned, it's the closest large galaxy to our Milky Way galaxy, but also it's part of what we call the local group of galaxies. There's a galactic cluster called the local group, which we're going to talk about shortly. In fact, why don't we talk about it very soon? First of all, galaxies, types and structures. So there are various types of galaxies and subgroups, but the main thing is there are three main types of galaxies. Your spiral galaxies here, which most of you are pretty familiar with this sort of shape. You have elliptical galaxies, which we'll talk more about, and we're also going to mention these irregular galaxies. So yes, there are subgroups, lenticular galaxies and all sorts. Don't get too confused by that. There are three main types of galaxies: spiral galaxies, elliptical galaxies, and irregular galaxies. Let's talk more about them. So spiral galaxies first up. There's that beautiful picture I never, ever get sick of looking at. Beautiful. So there's four main components of spiral galaxies. And I thought, let's start in the middle here. And these measurements here, these are the measurements given for the Milky Way galaxy. They often talk in parsecs here. If you ever see parsecs, a parsec's bit of a story behind it, but just a parsec is 3.26 light years. So the bulge for the Milky Way is about 6 parsecs, or about 20,000 light years across. And it's very densely packed with a lot of young and old stars. So there's star making going on in here, lots of young stars, lots of old stars. But the key here, it's really dense and super bright. Also of importance, at the center of most large galaxies, including the Milky Way, in the center of them, they have what they call a super massive black hole. So in comparison to your average black hole that we loosely talk about, that's called a stellar black hole. That's usually sort of in the order of sort of 2 or 3 or 6 or thereabouts solar masses. This one here in the Milky Way, you're talking it's over 6 million solar masses. So you're talking millions and sometimes billions of solar masses of these super massive black holes at the center of most large galaxies. And the Milky Way is no exception. And that's this little bit here, this bulge, that's what you can see here. And it's so bright in the Andromeda Galaxy, that's the smudge that we can see with our naked eye at 2.5 million light years away. Amazing. has a galactic disk, and that's what you see here in the Andromeda Galaxy. And that galactic disk is full of a lot of young stars, gas and dust, and that's where the star formation is going on. So there's loads of hot luminous stars. You can see gas lanes going through here, and that's all going on here in this stellar disk. And you can see the disk here, that's the 100,000 light years across that we talked about earlier on for the Milky Way. That's it going across there. And that's where you see all these really cool pictures. For example, these nebula. This is the Eagle Nebula, Emission Nebula, with these cool configurations of dense, dark dust and so on. It's also known as the Pillars of Creation. It's a very popular image from the Hubble telescope. And our good old friendly down south here, the Jewel Box Open Cluster. So that's all these images are taken in the Milky Way, in the disk, in this region here, the stellar disk of these spiral galaxies. That's where all the action is happening in terms of star formation and so on. Now, here we come to the stellar halo that I talked about earlier on. So surrounding this disk, you have this huge, big halo, spherical halo around these spiral galaxies. And as I mentioned, you don't really see it in images like down here below because it's sparsely populated with stars and the gas is very tenuous. But yes, it is there and it is important. And then surrounding that, again, you get a large, in fact, infiltrating really throughout the whole galaxy, the stellar halo, but even surrounding that too, it's there. There's a dark matter halo. Dark matter is the hypothesized particle in the universe that makes up about 30% of the presumed mass. We don't know and can see it yet, but it interacts gravitationally, and the evidence for it is the gravitational effect it has. In particular, when you look at the rotational rates of these spiral galaxies, those outer arms are traveling around a lot faster than they should be if that was the only mass out there. And essentially, quite loosely, it's quite cool how you mentioned that larger spherical of dark matter actually is the thing that really holds the galaxies, these spiral galaxies that are spinning around. It holds them together so they don't fly apart. So that, I just mentioned that there is another larger halo beyond it. But really, tonight's talk is really about the stellar halo. So, okay, so you know the Milky Way. I thought to just throw this slide in for a bit of fun. Where are we in the Milky Way? So you've probably seen this sort of figure frequently, and this is, they've mapped this out and helped with computer graphics and stuff with their observations, and this is our, to best of our knowledge, this is what the Milky Way would look like if you were removed, or say you were an Andromeda galaxy looking back at the Milky Way. That's the sort of structure we'd see. Our sun is sitting out about 26,000 light years from the centre, i.e. roughly about halfway. So here's the centre, here's the bulge, here's the centre of the galaxy. We're about halfway up towards that edge. And you might say, okay, let's just orientate ourselves. So if the sun's here and we're going around the sun on Earth, when it's the winter time here, we look on the southern hemisphere, because of the tilt of the Earth, the southern hemisphere, we look back to the constellation of Sagittarius, or the central bulge, and 6 months later we go around the sun and we start looking out to this part of the galaxy, and so on. And of course the northern hemisphere is different because of the axial tilt of the Earth. So just some general comments on spiral galaxies. They make up probably a little bit less than 30% of galaxies throughout the universe, it's estimated. They've got that flat disc-like shape, as I've mentioned. The light is more sort of evenly distributed throughout them. So if you were looking at, say, this galaxy here, it looks a little brighter here, but actually overall, the light is more evenly distributed when you're looking at a spiral galaxy from a distance. The range and size is relatively narrow. And for example, the Milky Way was yay big, and the Andromeda spiral galaxy was sort of yay big, about 40% bigger. That sort of is, that's the sort of ratios you tend to get. They tend to be within that sort of range, as opposed to you don't get a tiny little wee spiral galaxy and a really, really huge giant spiral galaxy. They're all within sort of a narrow range of sizes of one another. They've all got these developed systems of spiral arms. It's that interstellar medium. It's rich in gas and dust because of lot of active star formation is going on in these big arms of spiral galaxies. And that's really important point of spiral galaxies. That's where all of the active star formation is going on in the universe, predominantly in those spiral arms of spiral galaxies. So that's spiral galaxies. How about elliptical galaxies? Let's talk about those. So they make up greater than 60%. So by far they're the most common type of galaxy in the universe. The ellipsoid sort of shape, almost sort of like a rugby ball sort of shape. And this is the difference between remember I mentioned that the spiral galaxies are relatively evenly distributed in terms of light. Look at these. This is elliptical galaxy M87. It's a giant elliptical galaxy in the Virgo cluster, but you see it's really intensely bright in the central parts of the galaxy. Then it does drop off quite dramatically. The other thing you'll see with this, you don't see any highly structured spiral arms and stuff. No, it looks relatively smooth and generally featureless. And there's very little star formation going on. It's mainly old stars in these elliptical galaxies. As I mentioned here, so the range and size does vary. Remember, the spiral galaxies have a narrow range in sizes. The elliptical galaxies are the dead opposite. You can get tiny little wee dwarf elliptical galaxies, and then you get these huge giant elliptical galaxies, typically in the center of galaxy clusters. So they do vary widely. In fact, here I've got here, so the small ones might just have 1 million stars in them, which is not very many for a galaxy. And you get up to these real big sort of giant elliptical galaxies. You're talking 10 million. Actually, that's 100, isn't it? 100 million stars, 10 to the 13. So many more stars, so much of a wide range in size. So as I've mentioned, the stars tend to be older population 2 stars. They're more redder type of stars as opposed to the young blue stars. And that's why often spiral galaxies look a little bit more blue and elliptical galaxies look a little bit more sort of a reddish hue to them. You saw in the spiral galaxies how the spiral arms just go around the center, and that's the motion of the stars. Elliptical galaxies, totally different. It's really random orbits still around the center of the galaxy, but instead of going nice and smooth, it's just almost like bees humming, buzzing around a beehive. There's just stars going this way, stars going that way, stars going this way. They're all going around the center of the galaxy, but they've all got different orientation in the orbits, and some orbits are more circular and some are more elliptical. But the bottom line is it's just a random orbits around the center of the elliptical galaxy. Yeah, the other thing I've mentioned here, remember the interstellar medium for spiral galaxies, very rich in gas and dust, these new stars formation going on. Yep, the interstellar medium in these elliptical galaxies, very sparse, just old sort of stars, minimal star formation going. You don't really see gas and dust rings and arms going on here, not at all. Though I have got one interesting picture coming up to show you. Now, you'd probably say to yourself, where have I heard M87 before? Well, you did a short time ago, I think it was last year or the year before, that the Event Horizon Telescope showed us this first real image of the silhouette of a supermassive black hole at the center of a galaxy. That galaxy was the giant elliptical galaxy M87 that had its supermassive black hole had a mass of 7 billion solar masses. In other words, the size or the mass of our sun, multiply that by 7 billion. And that's the mass of the black hole at which they got the silhouette of through that Event Horizon image. So that's M87. That's I was showing you here early on in those images, in case you're wondering, where have I heard that before? So that's quite cool. Yeah, this is the interesting image. You might say, well, what's going on here? Clearly, this is an elliptical galaxy. So it's elliptoid sort of football, rugby ball sort of shape. It's really super bright here, and then it drops off quite a lot. It's got that red hue to it. But what's going on here? You've got a few little blue stars going on here. That, to me, looks like a dark gas lane, but I thought they only really occurred in spiral galaxies. But what's happened here in Centaurus A galaxy, sure, you've got your big giant elliptical galaxy, and it has sucked in the process of absorbing a dusty spiral galaxy. So I threw that picture in just for a bit of fun. I think it looks quite cool. Now, this brings us to our third type, irregular galaxies. They make up 10, 20, sometimes up to perhaps even maybe up to 30% of galaxies in the universe. They're commonly very, very small. They're deformed with no structure. So you don't get that lovely spiral disc shape going on, and you don't get that oval sort of red hue of elliptical galaxy going on. And because they're of low mass, they can be deformed and be attracted to things very readily, so they are prone to mergers and interactions. And of course, when they do interact with one another, or a large galaxy and so on, you get these what they call starburst regions, or areas of active star formation, because suddenly, you've got stars from different galaxies all coming together and getting concentrated, and gas gets concentrated, gets up to critical densities, and you start getting star formation. So these irregular galaxies are prone to mergers and interactions and are full of rich star formation, as you can see with this, but there's no form to it to talk about. So we've talked about the three different types of galaxies: spiral, elliptical, and irregular. And I've also introduced the idea of the local group of galaxies. So let's talk about that. So you've probably heard the term galaxy clusters and groups. What's all that about? Well, they really are similar terms. The galaxy cluster or group essentially is a gravitationally bound collection of galaxies. So a group of galaxies close enough to one another on cosmic sort of sizes, whereby they are gravitationally bound. One's not going to wander off and go to another sort of group of galaxies over here. They really belong together because of the forces of gravity due to their mass and due to their distances from one another. Now, there's two things. There's clusters, and that's the commonest term you tend to hear of galaxy clusters, but there's groups as well. And all it comes down to, it's pretty straightforward. Where you get up to 50 to 75 or thereabout galaxies, you call that a group. So in other words, a small cluster is called a group. And clusters are typically hundreds to thousands of galaxies. The local group has got more than 54. In fact, I glanced at the internet today just to see what the current count is, because they are discovering new and new sort of dwarf and small galaxies all the time as telescopes get more powerful and they can see these fainter galaxies. And I saw one paper this morning, it said something about up to 80. They're estimating there could be up to 80 galaxies in our local group. As I've alluded to, most of them are small dwarf galaxies. And as these large spiral galaxies like the Milky Way and the Andromeda, there's only one other, the Triangulum. So there's only 3 large spiral galaxies in our local group of galaxies, and the rest are all just small dwarf, irregular sort of dwarf galaxies. So let's have a look at these 3 spiral galaxies. First of all, yay, there's us, the Milky Way galaxy. That's us, guys. As I mentioned, they've done this isn't just some crazy diagram they've put together. They've looked at, particularly with radio telescopes, looked at hydrogen emissions, so they can see where the hydrogen dust lanes go. And they work out the velocity coming to us in various directions. They put that into computer models, and that's what they believe the Milky Way genuinely looks like if you were to see it as an observer looking back, say, from Andromeda. This is, of course, we've seen many times today, that beautiful, beautiful diagram of the Andromeda galaxy, M31. So that's our closest large galaxy, 2.5 million light years. And then there's the triangular galaxy, M33, and that's also a spiral galaxy. That's quite a bit smaller than the Milky Way at 100,000 light years across and 140,000 light years across. I don't actually have the figure on top of my head, but you guys can look that up. But that's also considered a large spiral disc-shaped galaxy, and the rest are all dwarfs. So the Milky Way and the Andromeda both have their own satellite galaxy systems. You saw in this picture back here, there's a couple of satellite galaxies of Andromeda, and the Milky Way's got quite a few. Of course, they're easier to spot with the Milky Way than other galaxies because they're naturally closer to us. And I just put this in here. These are some of the 4 most popular ones that people know about: the Large and Small Magellanic Clouds that we can see in the summer months from New Zealand quite happily. They look like that sort of wisps of cloud, a beautiful clear night. And you look up, you think, oh, I can see some cloud. They're actually the Large and Small Magellanic Clouds, which are satellite sort of dwarf galaxies. Then there's the Sagittarius dwarf galaxy, the Canis Major dwarf galaxy, and of course you get the gist of that. That's where the constellations, you can see them. So they're discovering more and more. There's lots of really faint ones out there, but the bottom line is the Milky Way and the Andromeda both have their own satellite galaxy systems. In other words, small hanger-oners that are just gravitationally bound to our galaxy very close. They interact with our galaxy and so on. Another topic, but that's, yeah, just you get the gist of it. Okay, so this is the spatial arrangement of the galaxies in the local group. So what they've done here, they've placed the Milky Way in the center. You can see the Andromeda galaxy out here. You see the little system here of dwarf galaxies. And here's the Milky Way with our little group of dwarf satellite galaxies. Here's the Triangulum. There is some speculation that the Triangulum may be gravitationally connected enough to Andromeda to call it a satellite galaxy, but I think that's up for debate yet. But let's forget that. So there's the three main relatively large spiral galaxies and all the rest of them. Now, a question you're probably having saying, well, okay, how far is it across from here to here? How big is the local group? It's about 10 million light years across. And you can see here it's quite sparse. These further satellites out here are a long way. Here's 2.5 million light years. Some of these galaxies are fairly further out from us, but at the end of the day, they are part of the local group. They are gravitationally, all these galaxies are gravitationally bound to stick together. So that's galaxies. And the other thing I want to talk about, we talked about galaxies, the different types and structures, talked about the local group. And the other sort of general principle that I wanted to talk about with, as a sort of using this study as a vehicle is quasars. And you've heard about quasars, may have seen it. You think, what are they? Well, in a nutshell, they're extremely bright, powerful, active galactic nuclei prevalent in the early universe. And that's what I'm about to explain shortly, but I just wrote that up there in summary. So they're from the early universe, active galactic nuclei, which we'll talk about, but you get the gist of it. That's the center of a nucleus, and they're really bright and powerful. So they're wonderful tools in astronomy. So let's have a closer look. So at the center, as I mentioned, at the center of most large galaxies lie these supermassive black holes, which, you're talking millions and sometimes billions of solar masses that the matter's just completely attracted towards. Light cannot escape. And the gravitational attraction is such that you get these large hot accretion disks, these big disks of gas that tend. So if you imagine, here's your galaxy. Then they've taken out here, there's the center of the galaxy. You've got this huge, big, supermassive black hole in the middle. You start getting these really hot gaseous and dust as well, accretion disks surrounding the black hole. And this is actually what they call a torus. So here's your gas cloud in here, and you get these big, dusty toruses around the supermassive black hole. And as the disks, the gassy disks, as the material starts falling inwards and inwards, and the gravitational energy being released is so great that high energy radiation is emitted out in these sort of bipolar sort of paths out here, and sort of huge jets of material, but also this big dusty torus here of dust and so on gets totally illuminated as well. And these sort of tori of dust, they are huge, massive. They glow from all this radiation being released, because you're dealing in just extreme numbers here with these huge supermassive black holes. And if you happen to be, say, us over here looking at this sort of configuration, we see this brightly glowing accretion disk and associated massive torus around it glowing from this powerful radiation that's occurring. We call that massively bright object a quasar. Bit of history behind the name quasar. It's sort of star-like is what it means, like a quasi-stellar object. So they're called quasars. A whole separate talk, but I just wanted to introduce that term to you. Think, okay, I know what a quasar is. It's just these at the center of a galaxy, supermassive black hole. It's started forming an accretion disk, and that's what they call an active galactic nuclei, I should have explained. So you get these supermassive black holes in the center of these big galaxies. A lot of the time, particularly more recent galaxies, or the ones closest to us, the the closer to us, the more recent we're looking at them in time, is a lot of those black holes are silent. They really don't have much going on around them. But the further you look back in time through, in other words, further away from us, you see these earlier galaxies. They are, the accretion, they've got big accretion disks, they're active, they're sort of stuff falling into the black hole, and all this activity is going on. And that's what they mean by active galactic nuclei when you see that term. And quasars are just extremely luminous active galactic nuclei. So that's an artist's impression which one might look like. Here's your supermassive black hole in the middle of this big galaxy. Here's the accretion disk that's getting really, really hot, radiating high energy, and all this other stuff around it, this torus, is all getting illuminated as well. And the other thing is that, these quasars are observed at high red shifts, which means that they're long, far distances and times away from us, meaning they're from the early universe. The earliest I think they've detected them so far is when the universe was only 690 million years old. That's what they can see these quasars back to. The peak incidence of quasars, the further you look back, you see a whole big stack of them, more and more as the further you look back, and then you start the numbers drop off again. So the quasars, sort of the numbers, appears to have peaked when the universe was about 4 billion years old. And to put that in perspective, we're about 13.8, say 14 billion years old. So you get the gist of it. Very prevalent in the early universe. You don't see them in the sort of more modern universe, sort of in our neighborhood. So that's quasars. So chapter 3. So you know what the Andromeda Galaxy is all about. You know what the local group of galaxies is all about. You know about the main types of galaxies. You've got it in your mind, okay, I know what a quasar is now. It's these just big, powerful, super massive black holes in these early, large galaxies from early universe that are really active and illuminating, and we can see them if we're looking at them face on. So we've got that background. So it was called Project AMIGA. It was published in August in the Astrophysical Journal, and AMIGA stood for Absorption Maps in the Gas of Andromeda. So here's our galaxy Andromeda, which we know this image really, really well now. It's nice big, there's its bright, super dense nucleus. There's the spiral arms of gas and dust for all the star formations going on. Here's some little satellite galaxies and so on. So what these guys did, they used the Hubble telescope. And the Hubble telescope's pretty cool because, it mainly sees an optical wavelengths, but it's got some instruments, in particular a couple of important spectroscopes that can look at light in the ultraviolet wavelengths. So what they did, they used the Hubble telescope and they observed 43 distant quasars from the early universe that are blazing out real high-energy light that happen to be in the line of sight of the Andromeda Galaxy. And I'll show that to you here. There you go. So here's these sort of distant quasars. Distant because we know that they're from the early universe. They're very powerful, so you see them reasonably good. So you've got 43 of them they found went through the line of sight in the vicinity of the Andromeda Galaxy. And it was ultraviolet light that was traveling from these. So it's high energy light traveling from these quasars that the Hubble telescope was observing with its ultraviolet spectroscopy. And what happened was that ultraviolet light, as it was traveling through and around the perimeters of what we can see with the Andromeda Galaxy, it was then absorbed, it ionized, in other words, it booted electrons. It was absorbed by certain elements in this sort of a spherical halo around and within the Andromeda Galaxy, which the spectroscopes were able to pick it up as an absorption spectra. So, in particular, what they were able to measure is the ionized states of silicon, carbon, and oxygen. And they, in particular, how those elements were abundant and how they were distributed throughout this stellar gaseous halo. So here's the structure. But remember, we talked about what you can't see in this image, this huge big halo around here of sparsely populated halo, sparse number of stars, and very tenuous gas. So using this method, they were able to identify the abundance and the distribution of silicon, carbon, and oxygen elements that this ultraviolet light from these distant quasars had ionized. So let's have a look at some results. So there's your little galaxy, Andromeda Galaxy here, what we see through our telescopes, the visible and the visible wavelengths and so on. And this is where your halo. And what they found was, you can see here, here's the quasars they study. For example, here, not much gas through here, not much gas through here. They identified a lot of gas through here. And when they mapped it out, they found the stellar halo extended up to 2 million light years from the Andromeda Galaxy. So here's your galaxy here, and this is going out to 2 million light years. There was still gas, detectable silicon, carbon, and oxygen gases around here in this halo. Amazing. So the other little comments here with their results, they found silicon, carbon, and oxygen was ubiquitous. It was readily abundant right throughout, the halo out to 2 million light years. Here's your little Andromeda Galaxy that we see visually, that we see the pretty pictures of here. You go out here, here's some of the quasars that they were looking at, the red dots, that's the quasars they were looking at. But they found that silicon, carbon, and oxygen was ubiquitous. So it was well distributed right throughout all this region around here, 2 million light years away. What they also found, not only was it much bigger than they thought, it was also more complex than they thought. And they actually identified 2 distinct layers of gas. There was what they call the inner layer of gas, which extended about 500,000 light years, and then the outer layer that went to 2 million. So here's your 2 million light years out here. It went out to about, there's a very complex, interesting, distinct layer about 500,000 light years around here. The outer layer was just very hot, so high velocity gas, high kinetic energies, but it was relatively smooth, this outer layers here, as opposed to this more interesting, complex inner layer of these gases around in the halo. So what is the significance of all that? Well, it obviously tells you that for that inner stellar halo, within that 500,000 light years, what would make that so complex and have sort of more complexity and different types of gases and stuff? The answer is it's clearly influenced by supernova activity in the disk. So here's your disk of your galaxy, and the speculation is that these heavier metals, silicon, carbon, and oxygen, that are produced inside massive young stars, that material, silicon, oxygen, and carbon, gets flung out into the inner sort of complex parts of the halo of the Andromeda Galaxy, and then probably falls or rains back into the disk. And that clearly illustrates that a recycling and dispersing process of newly formed elements is going on from the inner layers of the stellar halo. So it's not just all dormant out there. There's a lot going on within that 1/2 million light years across. The second sort of significance of the finding is that of course, as I've alluded to, is that it's much larger. The outer stellar halo goes out to about 2 million light years. And what did I say on one of those early slides? The Andromeda Galaxy is 2.5 million light years from us. And if its halo is going out 2 million light years, our halo probably is going to be going out somewhere in between 1 and 2 million light years as well. So what does that tell you? They're overlaying. Almost certainly the outer layer of the stellar halo of the Andromeda Galaxy is almost certainly overlapping and merging now with the outer stellar halo of the Milky Way galaxy. You probably maybe have read, otherwise I'll tell you now, the Andromeda and the Milky Way galaxies are coming towards each other. They're expected to merge in about 4.5 to 5 a billion years from now. That's the general calculations. They're definitely traveling towards one another. They will merge into a large elliptical galaxy in about 5 billion years. But here's the interesting point. Already, the outer stellar halos have already started merging. The merger has started. It's commenced, guys. It's going on right now as we talk. So how cool is that? Something to tell your family tonight if they're still around. So In a nutshell, the result was the Andromeda's halo is much larger and complex than expected. Interesting stuff. Lovely. Great stuff. Okay, so a little bit more about the significance of the study is what they've done now is they've given themselves a tool. It's now a proven technique or tool to study the halos of other galaxies in the local group. So they've done it now with the Andromeda galaxy over here. Hey, let's swing around, see if we can get some quasars in line with some of these other galaxies, see if they've got stellar halos. How large are those halos? How complex are those halos? What's the distribution of heavy elements from supernova explosions and so on? So it's quite exciting, and that there's a new, now proven technique or tool to study it. And the other one, of course, it's going to, by studying our neighbours, Andromeda Galaxy's stellar halo, which is sort of similar in appearance to the Milky Way, that's going to give us information on probably on what our own halo of the Milky Way is doing, because it's a very difficult region to study when you're actually within it. So it's easier to study your neighbour who looks very similar to you, look what's going on around him, and then try and correlate with your observations of the Milky Way. So it's also a tool to study our own Milky Way galaxy. So I just thought some images to revisit here after that little chat. So here's the Andromeda galaxy with the unaided eye, which is just that smudge from that bright super dense galactic nucleus. That's what it looks like that's what it would look like to us with an unaided eye if the spiral disk of the Andromeda galaxy was large enough, was bright enough rather for us to see. That's what it would look like. And are you ready? Check this out. Whoa, that's what, should we have magical eyes or something, but unaided with our eyes, should we be able to see, visualize that the stellar and gaseous halo around the Andromeda galaxy, that's what it would look like in the sky. Pretty cool, huh? So let's wrap up with some summary. So galaxies, there's three main types. Spiral galaxies with those nice disc-like structure, full of a lot of gas and dust and star formation going on. There's your elliptical galaxies, which are more sort of bland looking. They can be small or they can be very large, as opposed to spiral have a narrow range. You've got your irregular galaxies, which tend to be a lot smaller, deformed. They often have a lot of star formation going on because they often interact and merge with one another and with larger galaxies. So your three types of galaxies. Galaxies have large, massive outer gaseous halos that we don't see with our naked eyes. Why? Because they're too sort of sparsely populated with stars and the gas is too tenuous. But it's there, and it's important to know that it is there. Point number three, Andromeda Galaxy is our nearest large galaxy, which is part of the local group of about 80-odd galaxies that are all gravitationally bound. There's only three sort of reasonably sized spiral galaxies, the rest are dwarf galaxies, but Andromeda is our largest one, is our nearest large galaxy at 2.5 million light years away. And the merger, guys, has started. So distant, extremely luminous quasars, in other words, these really far away, which also implies early universe. Big galaxies had these massive, supermassive black holes, which were accumulating into hot accretion disks around them, which is generating a lot of energy. So you've got these really distant, extremely luminous, powerful, active galactic nuclei, in other words, active supermassive black holes, which we label as quasars. They now act as a tool to allow the halo of these galaxies to study with your spectroscopes and see what sort of elements are in there, how hot are the elements, how well are they distributed, and what elements are and where are they. So these quasars are wonderful tools because the distance and the power from the light's got to go through something for us to observe. So they allow us to study the halos. Spiral galaxies appear, in particular we're talking about the Andromeda galaxies, has a clear inner and outer halo, two distinct types of halos. That inner halo was complex, a lot of stuff going on, probably involved with a lot of recycling and distribution and dispersing of elements as supernova explosion occurs, and the disk spits out stuff to the inner halos and then it rains back down again. So that's an important part to understand how galaxies evolve, how galaxies function. And as we talked about here, the inner halo is far more complex and dynamic. Andromeda's halo is now starting to merge with the Milky Way halo, so that's quite cool. So the process has already started long before we're sort of seeing any visual changes ourselves. We've got to wait another 5 billion years for it to happen. No, it's happening now, guys. And we now have a tool and the ability to explore the halos of other galaxies in the local group, and that's the other exciting thing about this. We've essentially discovered a new tool. So a little bit of homework. So there's a couple of spectroscopes that are important on the Hubble telescope that they can study in ultraviolet wavelengths. So there's something, just go and have a look onto the Hubble telescope webpage, and there was 2 instruments. So find out and read up about those 2 instruments, in particular the 2 ultraviolet spectroscopes on the Hubble telescope. So that's pretty much, we've covered those topics. So the Andromeda Galaxy Halo, discoveries from a recent study. I hope you've enjoyed it. Thank you for watching, and I hope you've enjoyed it. So we can talk about perhaps some questions or something like that now, Steve.
Yeah, we've just got one question so far. We've still got some time if anybody wants to get in there real quick. We got one question from Felipe, who says, is it possible that satellite galaxies can clash with the galaxy they're orbiting?
Yes, absolutely. Philip, I think you're a new member, aren't you, Philip? Because I remember sending out your welcome pack, I think within the last week, if I recall. So welcome to the Auckland Astronomical Society, and thank you for joining in. Good question. The answer is absolutely, yeah. So they, for example, let's use the Large and Small Magellanic Cloud. They have nice big trails that they can see as they go around the galaxy, the larger Milky Way galaxy. So they're interacting all the time with little tails. They eventually, speculation is that we may absorb them and swallow them up. You're talking, I think, a few billion years down the line. But yes, large galaxies that have these smaller dwarf satellite galaxies quite happily cannibalize them. Yep, they slowly just rip them apart and just absorb and incorporate them into the larger galaxy. So the answer is yes, absolutely. And there is evidence for that going on right now with dwarf galaxies going around the Milky Way. Was that sort of the main gist of the question there, Steve?
Yeah, I think so. And Philippe, yeah, he confirms he is the new AAS member. So welcome, Philippe, and be great to see you as we get back to our meetings at Stardome, which we're hoping is going to be next week.
Yeah, so I've made tonight's talk sort of short and sweet. I thought 45 minutes or something like that. So I hope you've enjoyed it. And and some feedback of picking out a topic. That's what I've done. Picked out a study and then just used it as a vehicle to talk about astronomical principles. Yeah, sorry, Steve, I think I interrupted you there briefly. You were saying about we hopefully back in person next Monday?
Hopefully so. Keep an eye on the Facebook page and keep an eye on your email as to whether we'll be back next week or the week after. But we're hoping with Auckland moving into level 1 restrictions this week that we'll be able to get back to normal very, very soon. So that's going to be awesome.
Yep, and just looking forward, what we've got planned, assuming, all goes to plan, and we are doing in person next month, the introduction to astronomy is going to be on gravity. So one of our members, Dr. John Wishart, has got an interest in quantum gravity, and he's been chomping at the bit for about the last recent months to do that talk. So I'm going to talk on Newtonian and Einsteinian gravity for about sort of 30 to 40 minutes leading into it, and then hand the floor to John. He's going to talk about quantum gravity. So that's going to be really, really good. All going to plan. That's going to be in person at the Stardome the first Monday of November, which will be, let's have a look, Steve. That will be, the 2nd of November. So mark that on your calendar, guys.
We just got one more question before we finish up, and that's from Amir. And Amir wants to know, if the radio lobe of a quasar points at us, does it look interesting? Yeah,
okay, that's good question. I think most of those radio lobes, actually, I'm not a radio astronomer, so I'm just going by first principles, my understanding of it. Most of the interesting sort of looks for us to see a radio galaxy, those big lobes, is we're looking from a different orientation. Let's go back here. because I did show that, didn't I, in Active Galactic? We got time, so this is good. This is good. Okay, so here's your supermassive black hole, accretion disk, your big torus here, dusty torus. And when you're looking straight onto the torus, that's when you see these big quasars going on. And one of the principles here, which I think you're alluding to, Amira, is that it's the same process going on with these active galactic nuclei. In other words, active regions around supermassive black holes, is that it's the same process going on in all these different active galaxies that we're looking at, but some are labeled radio galaxies, some are labeled blazars, some are labeled quasars, and so on. And the general idea, current thinking, is that we're actually looking at the same process, but we're looking at it from a different orientation depending on which active galaxy we're looking at. And you'll see these big radio lobes, these sort of relativistic sort of jets of gas and stuff is blasting out here from both poles. And these big jets then start interacting with the intergalactic material, which then causes the emission in radio wavelengths, and you get these things are tens of light years across these big radio lobes here, and it's these high energy particles being spat out and ramming into the intergalactic medium, which then emits in radio frequencies. Now, I'm not a radio telescope astronomer, but my understanding is the best view of these radio lobes is when you actually look at it from a different orientation. You're looking at like here. If you're looking at straight on, often you'll see what they call blazars. It's a different type of active galactic nuclei again. But your best view to look at a galaxy and say, oh, that's a radio galaxy, because look at that big lobe, is because you're looking at it more side on. Oh, here it is down here. Actually, they've got the word blazar. Yeah. So if you're looking straight down the funnel at one of these, it tends to be called a blazar. And your radio sort of galaxies is more when you're seeing the lobe, because you're looking at it from a different angle, at a 180-degree angle. So I hope that's what you're referring to there, Mira.
And Suraj asked as a follow-up question, are those gamma ray bursts?
No, gamma ray bursts. There's a whole talk. That's good question though. Gamma ray bursts are cool. These aren't gamma ray bursts. Gamma ray bursts, there's two different types, of long and short duration, and it's crazy. You know, this is the sort of time frames you're talking that they're literally just quick bursts. They're a good descriptive sort of term. They are gamma ray bursts. The quick bursts, the short acting ones, short duration ones rather, are less than 2 seconds by definition, and they are thought probably to either colliding neutron stars, because then they split into two, repeating and non-repeating ones. The non-repeating ones are probably two neutron stars merging together to create another neutron star or black hole, which they're now picking up, of course, with their gravitational wave detector. And that will give a blast of high energy radiation just for less than 2 seconds, intense. And you know, gamma rays are the most highly energetic electromagnetic radiation / light there is. So it's quick, less than 2 seconds, burn, and that's a one-off. You can get a short duration gamma ray burst less than 2 seconds, and they are thought to be due that the hard crusts around neutron stars, highly magnetized neutron stars called magnetars, and sometimes the crust just moves a little bit and you get what they call a star quake. And that sudden release of energy on the surface of that magnetar, highly magnetized neutron star, gives out a quick burst of high energy gamma ray burst less than 2 seconds. And of course that process can repeat itself on that magnetar, so that's repeating. Then you get your long duration gamma ray bursts, which are greater than 2 seconds, and they are thought to be the final stages. It's when you get a supernova explosion of a really massive star. It goes supernova, and in the process you get a brief burst of gamma ray from bipolar jets of gamma rays from that imploding and then exploding star into a supernova explosion, which may then end as a black hole or a neutron star. And then there's things called hypernovae. Have a look into those too. Hypernovae, that's when you get really, 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 really massive stars, like 120 solar masses. And when they implode and explode as a supernova explosion, they give out really powerful gamma ray burst. So good question, but because often you think the two, but same process in terms of the long duration ones, same process, getting these big bipolar jets going out, but with these massive stars collapsing, it's just literally a burst of high gamma ray radiation. So it's literally a gamma ray burst, as opposed to these babies, it's an ongoing process, but I don't think that it's powerful enough to have ongoing gamma rays. Gamma rays tend to occur in quick bursts. So I hope that's sort of able to answer that one. See you next week. See you guys.